First example of our curve sketching question. Y equals 2 over x minus 4. So first thing I want to do is to work out x-intercepts. We set y equal to 0. Now if we have 2 over x minus 4 equal to 0, well, that's a problem we can't have. In a fraction, when we set a fraction equal to 0, we cannot have the bottom line equaling 0. So there are no x-intercepts. Y-intercept always occurs when x equals 0. Now in this case there is a y-intercept, so y equals 2 over 0 minus 4. That's 2 over minus 4, which is minus 1/2. So the graph cuts the y-axis at 0, minus 1/2. What we can do now is consider asymptotes. So what I didn't put in initially was a restriction on the domain of the function, but you can see that the function is undefined when x equals 4. So we have a vertical asymptote with the equation x equals 4. So what we want to do now is to consider what happens on the left and right hand sides of this asymptote. So as x tends to 4 minus, let's consider, so we want a number just to the left of 4, say 3.9. 3.9 take away 4 is negative. So we have positive 2 divided by negative, that gives us a negative value. Now, really, the value that we create here is a vanishingly small negative value. So 2 divided by a very small negative value gives us a very large negative value, which is to say, as x tends to 4 from the left, y tends to negative infinity. As x tends to 4 from the right, so a number that's just bigger than 4, take away 4 gives us a very small positive value. So 2 divided by a very small positive value gives us a large positive value, which is to say, as x tends to 4 from above, y tends to positive infinity. Now, what we have then, we have a vertical line representing the vertical asymptote. X equals 4. So to the left of 4 we have negative infinity, something like that, and to the right of 4 we have positive infinity. Now let's consider this function here. We don't have to do any division or simplification of this function because it's a proper rational function. The power of x, the highest power of x on the denominator, is higher than the highest power of x on the top. So we don't have an oblique asymptote, but what we can do is consider what happens to our function for very large positive and negative values of x. So as x tends to positive infinity, what happens? Well, the negative 4 is irrelevant, and we've got positive 2 on top, so 2 divided by a very large positive value is a very small positive value, which is to say, as x tends to positive infinity, y tends to 0 from above. So let's just say that again. When x is very large, the minus 4 is irrelevant, so we've got 2 divided by a very large positive number. That's a very small positive number, which is to say just above 0. What that means is that in effect y equals 0, which is the x-axis, is a horizontal asymptote. As x tends to negative infinity, y tends tends to 0 from below. So if x is very large and negative, again the negative 4 is irrelevant, so we've got 2 divided by a very large negative value, which is a very small negative value. Now, what we can do then is show horizontal asymptote at y equals 0. When x is large and positive, y tends to 0 from above. So we've got something like this here. When x is large and negative, the function tends to 0 from below. Now the next thing we want to do is to investigate stationary points. So I'm going to write this as 2 bracket x minus 4 to the power of minus 1 dy by dx equals, so it's minus 2 x minus 4 to the power of minus 2, and we'll write that as minus 2 over, and that equals 0 for stationary points. Now we've already been in this position, which is to say we have a fraction equaling 0, but the top line is what interests us. Remember, the function is undefined when the bottom line equals 0. So what we're really saying is, when does minus 2 equal 0? Well, minus 2 cannot equal 0. That means there are no stationary points. So here are the axes set up. We've got a vertical asymptote at x equals 4 and a y-intercept at 0 minus 1/2. Now let me just fill in what we know about the asymptote. Well, to the right of x equals 4, the function was tending to positive infinity, and to the left of x equals 4, the function was tending to negative infinity. For very large positive values of x, the function was tending to 0 from above. So what we had was something like that, and when x was tending to negative infinity, the function was tending to 0 from below. So we had something like this. Now you can see, I hope, what happens. We simply go through this y value here, and similarly we'll join up these two, and there is our function. If you want to check what you've done, please use the GeoGebra app. Second example. So let's consider x-intercepts. They occur when y equals 0. So x squared equals 0 and x equals 0. So we have an x-intercept 0, 0. Y-intercept occurs when x equals 0. So y equals 0 squared over 0 minus 2, and that's 0, which means we have 0, 0. Now when it comes to the asymptotes, what we need to realise is that we have an improper rational function here. So we have an x squared on the top and an x on the bottom. We need to carry out this division. So x minus 2 dividing into x squared. What do I multiply x by to get x squared? I multiply by x. So x times x is x squared, and x times minus 2 is minus 2x. Subtract, so x squared minus x squared is 0. 0 minus 2x is plus 2x. Now, we have an x here and an x here, so we need to continue the process of simplification. The question then is, what do I multiply this x by in order to get 2x, I multiply by plus 2. So 2 times x is 2x. 2 times minus 2 is minus 4. Subtract 2x, take away 2x is 0. 0 take away minus 4 is 4. So what I can do then is say that y equals x plus 2 plus 4 over x minus 2. So here is the original form. You can see there's a vertical asymptote at x equals 2. But this original form can also be written as x plus 2 plus 4 over x minus 2. Now if we consider what happens to the function as x tends to 2 from below and 2 from above. So a value slightly smaller than 2, say 1.9 or 1.99, well, we're going to have a positive value on top, but because we're subtracting 2 from it, we'll have a very small negative value on the bottom. So positive value on top divided by a very small negative value gives us a very large negative value, so we're tending to negative infinity. As x tends to 2 from above, what happens? So we have y tending to, well, let's just see. So 2.1 say, or 2.01 or 2.001 subtracting 2 gives us a very small positive value. We've always got a positive on top because of the square. So positive divided by a very small positive gives us a very large positive value. So vertical asymptote at x equals 2. So to the left of 2 we're tending to negative infinity. To the right of 2 we're tending to positive infinity. Now, the non-vertical or horizontal asymptote, it's absolutely necessary that we use this form here. So here in fact is the equation of the non-vertical asymptote. That's an oblique asymptote. So we use the abbreviation NVA, non-vertical asymptote, or you could say an oblique asymptote. It has equation y equals x plus 2. What we want to do is to consider what happens to the function as x tends to positive infinity and as x tends to negative infinity. And for that, this form here, the simplified form, is very, very useful. So for very large positive values of x, going in here, the minus 2 is irrelevant. So we've got 4 divided by a large positive value. That's a very small positive value. That small positive value is being added on to x plus 2. So what we have then is that y tends to x plus 2 from above. Now when x is large and negative, again the minus 2 is irrelevant, so we have 4 divided by a very large negative value, which is a very small negative value. Now that negative undoes the effect of the positive, so for what we have then is that y tends to x plus 2 from below. And I can make a rough sketch of what's happening. So here is our oblique asymptote, y equals x plus 2. So to the right, we're just above x plus 2. And to the left, we're below x plus 2. The fifth thing we want to do is to work out the stationary points. Now we can either use the original or the simplified version, it doesn't really matter. Let's just use the original. So we have a quotient. If we have u equals x squared, u dash equals 2x, v equals x minus 2, v dash equals 1. So dy by dx equals u dash v minus uv dash over v squared. So that's 2x times x minus 2 minus x squared times 1. And that's x minus 2 squared. So that's 2x squared minus x squared gives us an x squared on top, minus 4x. Now that equals 0 for stationary points. Remember, when we have a fraction set equal to 0, we're only interested in the top line. So what we have to do is to solve this simple equation. Take out a common factor of x. So x equals 0 and x equals 4. There are two stationary points. We've got our original function x squared over x minus 2. So when y of 0 is 0, we already know that. That means we have a stationary point at 0, 0. And then y of 4, well, that's 16 over 4 minus 2, which is 8. So we have a stationary point at 4, 8. Now, the next thing to do is to consider the nature of or investigate the nature of the stationary points. In higher, you would have drawn a nature table. We're going to do something different here. What we need here is a formula for the second derivative d2y by dx squared. We know that y equals x plus 2 plus 4 over x minus 2. I can rewrite that as and in fact it might have been better if we had used this form to work out dy by dx and d2y by dx squared. It's very easy to differentiate this, not just once but any number of times. So the x gives us 1, the 2 disappears being a constant. Bring down the power, so we have minus 4 and x minus 2 to the power of minus 2. Now we already have the stationary point, so we don't need to set that equal to 0 and solve. What I'm looking for is a formula for the second derivative. And this is where this form is very handy. So the constant disappears, we bring down the power, so minus 2 times minus 4 is 8. X minus 2 to the power of minus 3. and we can write that as 8 over x minus 2 cubed. So we have a positive on top and a cube on the bottom. Now, here is what happens. Rather than using a nature table, we know we have a stationary point at x equals 0. So d to y by dx squared equals 8 over, well, when 0 goes in here, we've got minus 2 cubed, which is minus 8. Now 8 divided by minus 8 is minus 1, which is less than 0. Therefore we have a maximum. So when the second derivative is less than 0, we have a maximum turning point. Similarly, when x equals 4, we have 8 on top and we have 8 on the bottom. 4 take away 2 is 2, 2 cubed is 8, so that's greater than 0. That means we have a minimum turning point. So the second derivative replaces the need for the nature table. So here is our setup, our x and y axes, and the oblique asymptote with equation y equals x plus 2, and the vertical asymptote with equation x equals 2. Now, we know that we have a maximum turning point at 0, 0. And at 4, 8, which is somewhere up here, we have a minimum turning point. We also know that the origin is both an x-intercept and a y-intercept. Next, now we can actually sketch the graph on just what we have here. If this is a minimum turning point, we can begin to sketch, and this is a maximum turning point here. We also know what happens at the asymptotes. So to the right of x equals 2, we're approaching positive infinity, and to the, as x gets very large and positive, we know that the function approaches x plus 2 from above. To the left of x equals 2, the function approaches minus infinity, so we have something like this. And as x tends to negative infinity, the function approaches the asymptote x plus 2 from below.